As AI applications grow in scale and complexity, so does the need for computing power that can handle massive amounts of data in real time. Traditional computing models, based on binary logic, have limitations in efficiently processing the types of tasks that neural networks excel at, such as image recognition, natural language processing, and complex pattern analysis. This is where neuromorphic computing, a groundbreaking approach inspired by the human brain, comes into play. Neuromorphic computing isn't just another incremental improvement, it represents a paradigm shift. With tech giants like Intel, IBM, and even universities leading research in this field, neuromorphic computing could revolutionize the way AI is implemented across industries. In this blog, we'll explore how neuromorphic computing works, its current developments, and the potential it holds for the future of technology. Neuromorphic computing refers to designing computer systems that mimic the way biological brains process information. Traditional computers work on a sequential step-by-step basis, processing binary data through transistors. Neuromorphic systems, however, operate more like the brain's neurons and synapses, allowing them to handle vast amounts of information simultaneously. The brain consists of billions of neurons that send signals to each other through synapses. In neuromorphic computing, silicon neurons and synapses function similarly, using electrical spikes to transmit data. This spike-based processing allows the hardware to adapt and learn over time, resembling human cognition. Key components include spiking neural networks, or SNNs. Unlike traditional artificial neural networks, which rely on continuous signals, SNNs operate with discrete electrical pulses. This spike-based communication is much closer to how the human brain communicates, making it faster and more efficient. Neuromorphic chips often use analog technology, which mimics the brain's continuous signal processing, rather than the digital on-off binary logic typical of classical computers. Neuromorphic chips function by enabling millions of artificial neurons to fire signals based on input data, just like biological neurons do. Instead of performing calculations in a centralized CPU, neuromorphic systems spread processing across a distributed network of artificial neurons. This structure allows the system to handle massive parallelism, processing multiple tasks and streams of data at once, improving speed and efficiency. Since neurons only fire when needed, neuromorphic systems are extremely power efficient compared to traditional CPUs and GPUs. Unlike standard AI models that require cloud-based training, neuromorphic chips can learn on the device itself, opening possibilities for adaptive IoT devices, wearables, and edge computing. Several leading tech companies and research institutions are developing neuromorphic hardware, making significant strides toward mainstream adoption. Intel's neuromorphic chip, Loihi, is designed to enable real-time learning with remarkable energy efficiency. Intel has been using Loihi to explore applications such as autonomous navigation and complex pattern recognition, showcasing its potential for use in robotics, smart sensors, and IoT. IBM is heavily involved in neuromorphic computing research, particularly with its True North chip, which contains over 1 million neurons. IBM's work focuses on integrating neuromorphic processing in areas like machine vision and image classification. Academic institutions are also leading groundbreaking research. Stanford's NeuroGrid and MIT's neuromorphic computing initiatives aim to develop chips that can learn and adapt in real time, potentially powering next-gen devices like autonomous drones and human-assistive technologies. Neuromorphic computing has the potential to transform industries that rely on real-time data processing, complex pattern recognition, and adaptive learning. Here are some of the most promising applications. 1. Healthcare. Neuromorphic chips could power smart medical devices, enabling them to analyze complex biological signals, like brain activity, in real time. This could lead to advancements in brain-machine interfaces, aiding patients with neurological disorders. 2. Autonomous vehicles. Real-time decision-making is crucial for autonomous cars. Neuromorphic systems can process vast sensory data faster and with lower power requirements than conventional systems, improving both the safety and efficiency of self-driving technology. 3. Robotics. Robotics applications require fast reflexes and adaptability. With neuromorphic chips, robots could learn from their environment in real time, responding to unexpected changes in their surroundings with human-like flexibility. 4. Edge AI devices. With their low power consumption, neuromorphic chips are perfect for IoT and edge devices that need to process data locally. From smart security cameras to wearable health monitors, these chips could power intelligent devices that learn and improve over time. While neuromorphic computing holds incredible promise, it is still in its early stages and faces a few challenges. First, hardware development. Building reliable and scalable neuromorphic chips remains complex and costly, as it requires entirely new manufacturing techniques. Second, software compatibility. Current AI software is designed for traditional architectures like CPUs and GPUs. Developing software that can efficiently operate on neuromorphic hardware is an ongoing challenge. Third, scaling neuromorphic systems. To truly mimic the human brain, neuromorphic chips need to scale to billions of artificial neurons. This would require advances in chip design and fabrication. However, with sustained investment and research, these challenges are being actively addressed. Many experts believe that neuromorphic computing could become mainstream in the next decade, potentially transforming how we interact with AI across all domains. Neuromorphic computing is a brain-inspired technology designed to mimic neural activity, enabling AI systems to perform tasks faster and more efficiently than traditional architectures. Spiking neural networks, or SNNs, and analog components are at the core of this technology, allowing real-time, low-power data processing. Intel, IBM, and academic institutions are at the forefront of neuromorphic research, pushing boundaries in areas like healthcare, autonomous vehicles, and robotics. Despite current challenges, neuromorphic computing is poised to reshape AI as